welcome to this video on A-level chemistry. This is the CIE Pass paper, and the exam was the June 2014 paper, or May, June 2014. The code for this one is 9701/43. So if you have the paper in front of you and you printed it off, then you can go through the paper and you can obviously check back on this video to see what the answers are. But crucially with this video, we're not just going to say what the answers are, because obviously you can have a look at the mark scheme for that. We're going to try and explain why that is the case, to help you understand why it's the answer. And then you can actually learn from it as well. So you can get the obviously the exam technique, and you can learn from it as well, which is absolutely brilliant. You can see on the left-hand side of the video there's a series of links, and that allows you to skip to different questions. So you don't have to stay on question 1. You can move to question 7 or question 6, for example. So you don't need to watch the whole video. You can skip to different parts. So we just click on them links there, and it'll take you there. They'll be there throughout the whole video as well. So this paper is out of 100. There's 100 marks up for grabs, and there's 8 questions in total. So it's quite a big paper, and they give you a couple of hours to do it as well. So right, so let's make a start. So question 1. And it starts by saying, state how the melting point and density of iron compare with those of calcium. So we're looking at the melting point of iron. If I bring in our periodic table, so we can see here, there's iron there, and there's calcium, which is over there. You see iron is obviously got more protons than calcium has. So this is actually going to have an effect, because they're both metals. So metallic bonding has your metal ion, and it lined up in rows, and then we have delocalized electrons over the top of them. It's a little bit like a duvet cover, I suppose. So and these are attracted to the positive metal ions. Now iron has more protons than calcium, so there's going to be a stronger attraction between the delocalized electrons of iron than there is calcium. So that's going to give it a much higher melting point. And just on the on that as well, because it's going to talk about densities in the next question. So iron is also going to be more dense than calcium because it has a bigger atomic mass, as you can see on there, and the radius of iron is actually smaller. We have a much smaller radius, so it's a smaller radius and it's a bigger mass, so that's obviously going to make it more dense than something like calcium, which is slightly bigger. Again, the smaller radius is because of the increased pull from the nuclear charge in the nucleus from iron compared to calcium, which has fewer protons. So let's pull that away and let's get an answer down in here. So it's going to talk about, so the melting point of iron we said was higher. So we're just going to put that in there. And the density is higher as well in iron. And then obviously this is the explanation. So the melting point, the reason why, again, we said we had a stronger attraction between cations, which is the metal ions, and electrons. All right, okay, so and then the density, we said the reason why is because it had a greater AR, or atomic mass, and smaller radius. You must include both of them, because obviously density is about how much mass you can get in a specific area, and the bigger the mass in the smaller area, the higher the density. So these two are very, very important, so you must mention both of them. All right, so you get 4 marks for that, which is not really too bad. It's not a bad start, really. And so the marks come in here. So we've got higher, obviously 1 there, 1 for saying that, 1 for saying that, and then, whoops, 1 for saying that as well. That's my camera, just let's get that settled. Okay, right. Okay, right, so on to the next part. Okay, so this is B. So just nudge that up there. Right, so it says the following diagram shows the apparatus used to measure the standard electrode potential, so E0 of a cell. composed of a Cu2 and Cu electrode and an Fe2 and Fe electrode. So it says finish the diagram by adding components to show the complete circuit. Label the components you add. Right, so this is obviously showing a battery. So we've obviously got two half cells here. So the thing that we need is a voltmeter. So we're going to put that in there. Just going to connect that up there because obviously you need to measure the cell potential across there. And also we're missing a salt bridge. So let's just add that in there. So salt bridge, because obviously your cell would not work without that salt bridge. And this is your voltmeter. A little bit of physics there. Right, okay, so you get 2 marks for that. And that's the only things that are missing. So let's mark them up. Make sure we've got the right ones there. So we've got voltmeter and salt bridge. There we go. Right, and this is in the spaces below. Identify or describe what the 4 letters A to D represent. Okay, so we have, it says copper and an iron electrode. So we're going to label these here. And really it doesn't matter which way round they are. But I'm just going to put in copper as A. So with these cells, you must have the metal, because this is remember this is a metal and it's ion. That's how you make these electrodes. So how you make these half cells. You must have the metal, solid metal, or the solid version of the ion that's in here. Sometimes you don't though. So for example, the standard hydrogen electrode, you have to use, obviously you've got H plus and H2, but obviously neither of them are solid. So you have to use a metal that will conduct electricity, and normally that's platinum. Platinum's inert, so it doesn't react with anything, and it's a good conductor of electricity. So if you've got a situation where you have 2 ions that make up your cell, then you have to use an electrode which is inert and is a good conductor. So for example, platinum. But in this case, we do have the metal version of the ions that we've dissolved it in, so that makes it a bit easy. So okay, so we're going to start with A. So we'll say this is copper, for example. Again, it could be the other way around. There's no real preference. So we'll just say that one's copper metal, which is there. But this is important. Copper metal must be submerged or dunked into the solution, and the solution must contain copper 2 ions. So the normal chemical you use is copper sulfate. That will give us a supply of copper 2 ions. So I'll just put that in there while we're here. So this is going to be copper sulfate. So we'll put that there. Copper sulfate is CuSO4. So you could say that, and that will provide your 2+ ions. And crucially though, because this is standard electrode potentials, we have to give the concentration, and these concentrations are always at 1 moles per dm cubed. So that's very, very important. And then B, obviously B is a metal. This one's going to be iron. This is going to be iron metal. And D is going to be the solution that it sits in. Again, it's just going to be something like iron sulfate. And that's going to give us our Fe2+ ions. So let's just write that there. FeSO4. There you go. And again, we must include the concentration. It's very important. You've got to be really specific. If you miss these out, you won't get the mark. So this one was actually worth 3 marks. And you get 1 mark for stating your concentrations for both of them, 1 mark for giving your copper sulfate and iron sulfate as well, and then you actually get 1 mark for these 2 here for correctly identifying your metals. Again, these could be either way around, but the copper metal must be submerged into the copper sulfate. That is very, very important. Okay, right, so there we go. Right, on to the next part. Right, okay, so let's just put that down. There we go. Right, okay, so it says part 3, use the data booklet to calculate the E0 for this cell. Right, so what I've done is I've gone away and had a look at the data booklet, and I'll just bring it into here, and I've highlighted the 2 bits that we need to look at here. So if I just bring that into shot, there you go. Right, now the ones we're looking for is obviously the Cu2 plus the 2 electrons in copper. Which is this one here. You can see Cu2 plus 2 electrons gives copper, and that's plus 0.34. And then we've got the iron one as well, which is this one here. There you go. Fe2 plus 2 electrons will give Fe. Now notice this number is negative. This means that this reaction is unlikely to proceed in its current form here, in the reduced form. The ones which are positive suggest that this reaction is favourable. So what we do is when we actually work out the E naught of the cell, we take the two values and we do the E naught of the positive value, which is this one, 0.34, minus the E naught of the negative value. And obviously a minus and a minus will turn that into a plus. So that's going to be effectively 0.34 plus 0.44, and that will give us our E naught of our cell. Okay, so we'll come back to them as well in a minute. Right, so the E naught of our cell, there's our data book that we use that. I'm just going to put that there. E naught of the cell equals 0.34, and that could be minus minus, which effectively turns it into a plus 0.44, because remember that was minus 0.44 on there, and that would equal, let's just bring that in there. Okay, so we've got 0.34 plus 0.44, and we should get 0.78, and obviously that's going to be in volts. Okay, so that's the E naught of our cell. Right, and then it says predict how the size of the overall cell potential would change, if at all, as the concentration of solution C is increased. Right, so solution C in my example was copper, but it doesn't really matter. It could work with either of them, to be honest. So let's just bring this back in again. So here's our arrows. Now what I'm going to do, I'm going to use something called the anti-clockwise rule. This might hopefully explain what's going to happen. Right, so if I just take that out. Right, I've got two half equations here. Okay, and what we can do is we can do what we call an anti-clockwise rule, which shows us which way the reaction is going to go. Now we must always put the most negative on the top. And effectively what we're going to do is we're going to do something called an anti-clockwise, and this will show us what reaction is feasible. So if I write my overall equation here, so effectively the overall equation is going to be Fe, which we start from here, cancel the electrons out, and that's going to react with Cu2 plus, which is down here, just note that up, which is going to react with Cu2 plus, which is there, and then we're going to that's going to produce, put that there, that's going to produce Fe2 plus, which is on this side, and it's also going to produce copper as well. Right, so if we effectively increase the amount of, this is the overall equation here, but if we increase the amount of copper, because in solution C mine was copper, you can see here Cu2 plus, sorry, if we increase the amount of this, then what's going to happen is this is going to push, use this up according to Le Chatelier's principle. So if we increase that, the reaction is going to shift to try and use it up, to try and do the opposite, and effectively that's going to push equilibrium to the right, and we're going to produce more copper as a result. This is then effectively going to increase this number and make it even more positive because it's moving even further in the right hand side. It's the same with the iron one as well. Now you can look at this in two ways effectively. If I increase the amount of iron, this is effectively going to push it that way towards the Fe, but it's going to make this number more negative. And so if this number is more negative, then this is effectively going to make your E naught of the cell, the overall cell, more positive as a result. So if I just come back to this, so you can see this number here is minus 0.44. If this number gets bigger, then this number is going to get bigger as well. And it's the same with this number as well. This is the one for copper. So either way, it actually seems to add up. So it doesn't really matter which one you put as C. But because I've used copper, I'm just going to describe it as copper. But that's quite a tricky one. So I'm going to put, as we increase, I'll just put that on there. You'd have to write that out properly though, obviously, because that might be a bit ambiguous. As we increase the concentration of Cu2 plus, the E naught of the copper 2 plus / copper electrode increases. So what that means is that overall cell potential would increase. All right, okay. So you get just look at these ones here because I know they don't really break up the marks for these ones. You get 1 mark for this, 1 mark for saying that actually this would increase, and then the effect of the E naught of the cell. So basically, if we increase any of these numbers here, we get a bigger value here, and so that's going to make it more likely to occur. Right. Okay. So C. All right. Okay. So okay, so this is numbers up there. Right, so this is C. It says the iron 2 complex ferrous bisglycinate hydrochloride is sometimes prescribed in capsule form to treat iron deficiency or anemia. A capsule containing 500 milligrams of this iron 2 complex was dissolved in dilute H2SO4 and titrated with 0.0200 moles per dm cubed potassium manganate. 18.1 centimeters cubed of potassium manganate solution were required to reach the end point. And it says the equation for the titration reaction is as follows. So you can see we've got it here. So it's describe how you'd recognize the end point of this titration. Right, the manganate, what you would see is in your actual conical flask, you'd have a colorless solution. And then when you add your manganate, it would go pink when you reach the end point. So this is just put that in there. So it would go colorless to pink. Go. So that's something classic permanganate reaction. Right, and then it says calculate the number of moles of Fe2 plus in the capsule. Right, so what we need to do is we need to work out basically the number of moles of manganate first, then use our equation to work out the number of moles of iron. We can only work out the number of moles of manganate because we have the concentration and we have a volume as well. So we're going to just work that out first. It's like kind of like an indirect way. I'm just going to drag that down so we can see it. Right, so we're going to put MnO4 minus. So this is the number of moles. And we're going to take the concentration, which is going to be 0.02. We're going to multiply that by the volume that was needed to reach the end point, which is 18.1. 18.1. And this is going to be, we have to get that into decimeters cubed. So one way in which we can do that, because that's in centimeters cubed, is to just do times 10 to the minus 3. That's the same as dividing by 1,000. So it's just a quicker method, really. Right, so if I bring in our calculator. Okay, so we have, let's just put that over there. Right, 0.02. Multiply that by 18.1 times by 10 to the minus 3. Which is effectively the same as divided by 1,000. 3.62 times by 10 to the minus 4. Times by 10 to the minus 4. And this is moles. Okay, so now we've worked that out, we can now work out the amount of Fe2 plus. Because we have a 1 to 5 ratio here, this is the number of moles of manganate. So the number of moles of iron, Fe2 plus, is going to be 5 times the number of moles of this, because it's 5 to 1. So it's pretty straightforward. 3.62 times by 10 to the minus 4. Multiply that by 5. And that will tell us the number of moles. So let's just bring the calculator back in. Okay, right, so it's going to be 3.62 times by 10 to the minus 4 times that by 5. And that's going to give us 1.81 times by 10 to the minus 3. Okay, and that's moles. So with that, you get 1 mark for that bit. Let's just stick in the mark there. There you go. And then it says we need to work out the mass of iron in the capsule. Right, so a way in which we do that, we need to obviously work out the mass is obviously the number of moles times by the MR. So that's just a pretty straightforward mole calculation. So the mass or the MR of, or the AR, not the MR, the AR of iron, let's just bring that in, is 55.8, as you can see. So we're going to put 55.8, and that's going to multiply out by the number of moles. And I've just worked this out here. So that's going to be 1.81 times by 10 to the minus 3. That's going to go there. And then we're going to obviously work that out as well. So let's just put that in. So that's 55.8 multiplied by 1.81 times by 10 to the minus 3. and that should give us this number here. So I'm just going to round that. I'm going to call it 0.101 grams. There you go. Right, and so obviously that would get you a mark as well. So marks away. So marks for that one and marks for that one as well. Right, and then the final step, what they want you to do, let's just nudge that up. Okay, is it says the molar mass of the iron 2 complex, assuming 1 mole of the complex contains 1 mole of iron. Right, so the MR, this is the molar mass or the molecular mass, is effectively the mass in grams divided by moles. Okay, so effectively the mass, it said, if I just come back up to here, the capsule contains 500 milligrams of this complex. We need to convert that into grams, so we effectively divide that by 1,000 to get it into grams. So that's going to be 1, 2, 3, going backwards, 0.500 grams, because it must be in grams. That's the first thing. Don't forget that bit. A bit sneaky there. That's it. And then we're going to divide that by the moles. Obviously, we know the moles. That's just 1.81 times by 10 minus 3. And then let's bring the calculator back in. 0.500 divided by 1.81 times by 10 to the minus 3. And there we go. 276.2. All right, and then you get obviously a mark for that as well. So you get 4 marks in total for that question. And there we have it. That's the end of question 1. So let's look at question 2. Okay, so this is question 2. And question 2 starts by saying the ions of transition elements can form complexes by reacting with ligands. State what is meant by the terms complex and ligands. Right, so complexes are these massive molecules with metals in the middle of the metal ions. And they're actually surrounded by lots of ligands, which are molecules that will have a lone pair of electrons, and they form a dative covalent bond into the metal ion. So right, so let's write this down. So we have let's put this down here. So this is a compound with a central metal ion surrounded by one or more ligands. And then obviously we'll come on to the ligand, and a ligand is a species that contains a lone pair of electrons and crucially it forms a dative covalent, or we can also call it coordinate as well, coordinate bond. Dative covalent bond to a metal ion. Right, so you get 2 marks for that. So this is just basic definitions really that you need to try and remember. So obviously you get 1 mark for saying what the complex is, and then 1 mark for obviously saying what the ligand is as well. Okay, right, on to the next part. So this is part 2. Right, so question 2. Okay, so part 2, it says 2 of the 3 complexes formed by copper are CuH2O6 2+ and CuCl4 2-. Draw 3-dimensional diagrams of their structures in the boxes and name their shapes. Right, okay, so we have the 2 different substances here. This one is CuH2O6 2+. This means because it's got 6 waters surrounded by copper, this is going to be an octahedral shape, so we need to draw something octahedral here. This one, CuCl4, you need to know that this one is a tetrahedral shape, so we need to draw a tetrahedral shape there. So because we're talking about 3D shapes, we need to draw our wedges and dots and things like that. So right, let's start with this then. Right, so copper is Cu in the middle, we have H2O there. If you can help it, try and draw it where the bond is actually onto the oxygen here. The data covalent bond. It's just because it's actually technically correct if we do it that way around. Okay, so we've got two of them coming out here. We have a wedge coming out there. H2O with a dotted line. H2O. Right. The whole thing is in square brackets because it's a complex, and we put the charge. It's a charged complex. We've got copper 2 plus, and that's it there. So we have two going away, two coming towards you, and two in the plane of vision. So it must be drawn like that. It's very, very important. And the shape we said was octahedral. You go. This one is tetrahedral. So we have one going along here. This is Cl. We have a dotted line going here. Again, it doesn't really matter which way around these three go, but it must be shown in this kind of general shape. The wedge, we must have a wedge there, which is the Cl, and then a one in the plane of vision. So we must have two in the plane of vision, which are represented by the solid lines, one coming towards you and one going away. And it's like this, looks like a tripod effectively. It's the best way to describe it, like camera tripod. So there's the tripod legs, and there's the stand that the camera would sit on. So this is 2 minus. There's my photography knowledge coming in. This is a tetrahedral. There you go. Right, so we get 3 marks for this. So we get 1 mark for this one, which is here. We get 1 mark for this structure, and we get 1 mark for the names. We need both names to get the mark there, that last mark there. Okay, right. Okay, so on to the next bit, which is part 3. Okay, right, so it says platinum forms square planar complexes in which all 4 ligands lie in the same plane as the platinum atom. There are 2 isomeric complexes with the formula PT-NH32Cl2. There are 2 isomeric, suggested structures of the 2 isomers, and by comparison with a similar type of isomerism in organic chemistry, suggest the type of isomerism shown here. Okay, and we have 2 different structures of the isomers here. So we've got isomer 1 and isomer 2. Okay, so isomer 1, this is the cisplatin, this thing. So we have cis and transplatin. So we have one where the Cl's are here, and then the 2 wedges come out here. So this is the anti-cancer drug, this one. Okay, so this is the cis one here because they're on the same side. And then its isomer is the trans version. So we have Cl, we have NH3 over here. We have a wedge down here, NH3, and then a wedge down here. Which ones are terrible? That's Cl. Okay, and then the type of isomerism is geometric. Okay, and this is cis-trans. Perfect. Right, so we get, how many marks do we get for this? We get 2 marks. We get 1 here, and we get 1 here. And so obviously all that adds up to 7 as well. Okay, right. Okay, so on to the next part. There we go. Right. Just drag that down there. Right, so it continues, and it says copper forms 2 series of compounds, one obtaining copper 2 ions and the other containing copper 1 ions. It says complete the electronic structures of these ions. So we've got copper 2. Right, so I'm just going to grab this periodic table. Copper is, there it is. Okay, so copper's there. So it normally has an electron in the s orbital, and it has 9 in the it has 1 in the copper here. So it actually has 10 in the d orbital, and it has 1 in the s orbital, which is in here. So if this is copper 2, what we're going to do is we're going to remove an electron from the s orbital first, then we're going to remove one from the d orbital, which is going to leave us with 3d9 for copper 1. And for copper 2, because remember copper 2 is one of the exceptions where it has a full 3d orbital and it has 1 in the s. So copper 1, effectively you remove the s first before you remove 1 from the d. So that's going to be 3d10 for copper 1. So that's really important. You've got to understand that copper actually has 10 electrons in the d orbital and 1 in the s. So it's one of them exceptions. Okay, so let's just write this down on here. Okay, so this is going to be 3d9 because obviously you have the configuration of argon first, and this one is going to be 3d10. So that's going to go there. Okay, right, and then it says use these electronic structures to explain why copper 2 salts are usually coloured. Right, the main thing which makes transition metals coloured is that they have, when the ligands are attached to them, their d orbitals actually split. We get d orbital splitting, and basically that allows electrons in the lower orbitals of the splitting to effectively be promoted to higher energy levels. And effectively when it does this, it absorbs a photon to do that, and this gives it this colour, obviously that's emitted. Now, if you didn't have any space in the upper orbital, or all the orbitals were full, then you wouldn't get any colour, and you get a non-coloured compound. So we're just going to put this in here. So these copper 2 salts are coloured. We've got 3d9. That leaves us with a space in one of the d subshells. So that means that we can have actually a coloured compound, but this one's full, as you can see here, so there's no space for any electrons to move between lower and upper orbitals. So, right, let's write this down anyway. So we've got d orbitals are split, and the electron moves from lower to upper orbital, and it absorbs. So as a result, obviously this is how it does it. So, and it absorbs a photon. A photon is like a little packet of energy, in the form of light energy in this case, and that's what we give this. That's why we see this this coloured compound. So we get 2 marks for that bit. We need to say 1 mark for saying that we have splitting first, and then the absorption of a photon is very important because this is obviously what gives it its coloured appearance, is that it will absorb this photon. That only happens, like I say, when you've got a partially filled d subshell. If it's full, you don't get any coloured compounds, so that's quite important. And then the next bit here, it says copper 1 salts are usually white or colourless, and again, the reason why is because we said all orbitals are full. There you go. Right, so we get 5 marks in total for that. Obviously, we've got the 2 there. You get 1 for this one, which gives you 3, and then we get 1 there and 1 there as well. So we get 5 marks in total for that one. Right, on to the next bit. Quite a big question. Right, okay, so it starts by saying, it says C, copper 1 oxide and copper 2 oxide can be both used in the ceramic industry to give blue, green, or red tints to glasses, glazes, and enamels. The list of the enthalpy of formation values for some compounds. So we've got the different compounds here with the enthalpy of formation. It says copper 2 oxide can be produced in a pure form by heating copper 2 nitrate. Use suitable HF values, or delta HF values, from the table to calculate the enthalpy for this reaction. Okay, so this is screaming out Hess's cycle. I think the cycles help because it just gives you a lot of clarity as to kind of how you work. Now, because we're doing a formation, we're going to draw arrows pointing up, and formations from elements in their standard states. Again, we don't need to worry about balancing at this stage down here. As long as the top equation is balanced, that's all that matters. So here's our elements here. And then what we're going to do is look at the formation of CuNO32. So the formation of CuNO32 is minus 302.9. Okay, so here, obviously, we've only got one on that side. This one, we've got the formation of CuO, and that's going to be minus 157.3. Okay, and then we've got the formation of NO2. We have two of them though, so we need to double that. So we need to have 2 times by, and that's going to be plus 33.2. And obviously that's going to give us 66.4. So there's our two numbers there. And then what we have to do is add these two together. So let's just bring in our calculator. So we're going to have minus 157.3, and we're going to add that to 66.4. That's positive. And that's going to give us minus 90.9. Must be the sum of both of them. Notice the oxygen though, we don't have a value. The enthalpy of formation of elements is zero, is always zero. So that's why we don't have a value here. So if you're wondering why we haven't included that, that's the reason why. Okay, so then all we do is we use our cycle and we need to work out this bit. This is the enthalpy of reaction, that bit there. So we want to work out this way, the value going this way, but it's like a roadblock. We can't go that way. So we have to go against the arrow here, like a diversion, and we go with the arrow here. When you go against the arrow, you effectively flip the sign. So that's going to be 302.9. There you go. And then we go with the arrow here. So that's keep the sign the same. So that's going to be minus 90.9. And that's going to give us 212. And that goes in there. All right. So we get 2 marks for that. So it's not bad. Okay. And then if we move to the next bit, it says copper 1 oxide can be produced from copper 2 oxide. Use suitable HF values, again, to calculate the delta H of the reaction. Right, so we have to do exactly the same again. So let's just quickly drop the cycle. Copper plus oxygen, because they're the only two that we have there. Right, we're going to form CuO. CuO had a value of, if we can just see it there, CuO is minus 157.3. But we have 2 of them, so we need to do 2 times by minus 157.3. Bring in our calculator. So it's 2 times by minus 157.3. And that's going to give us minus 314.6. There you go. Right. And on this side, we're going to form copper Cu2O. So I just quickly drag this down there. See, that's the value there, minus 168.6. So let's just write that down in there. 168.6. Again, we don't need to form oxygen because it's an element, so we don't have any value for that. And again, we do exactly the same thing. We need to work out this bit. So we're going from here to here. We need to go against the arrow here with the arrow here. Against the arrow changes the sign. So that's going to be 314.6. 314.6. Okay, so we've got there. And then we're going to subtract that because we're going with the arrows. So we keep that the same from 168.6 and we get 146. Which goes in there. Now, because you've already worked out a Hess cycle before, they're only giving you 1 mark for this one, which is a bit mean of them. But yeah, so we've got 3 marks for basically 2 Hess cycles. Right, and then the last bit here, it says, hence suggest whether a low or high temperature of oxidation would favour the production of copper 1 oxide, and we need to explain our reasoning. Now, this is the formation of copper 1 oxide. So your copper 1 oxide is going to be this one here. Now you can see the formation of both of them, both of these ones here, are actually endothermic. So we make the copper 2 oxide first, that's endothermic, and we make the copper 1 oxide is also endothermic. So actually by heating this up, this will encourage the reaction to move in the endothermic direction, which will then obviously allow you to produce more copper 1 oxide. So it's just Le Chatelier's principle. So we're going to obviously write down our answer here. So we say high temperature is needed. Oops, if I can spell. Temperature. There you go. As the delta H, which are these 2 numbers here, is positive, and so is endothermic. So yeah, endothermic reactions, heat them up, and they will obviously produce more products as a result. So there we go. It's up 16 marks, as you can see in the bottom there. So it's a big question. Right, on to question 3. Okay, so this is question 3. Question 3 is looking at piperine. Is the compound responsible for the hot taste of black pepper. So we've got the big molecule here. It says piperine is an amide and can be broken down as follows. And you can see we've got the piperine molecule here. It's broken down into piperric acid and piperidine, which is this molecule here. Now it says suggest reagents and conditions for this reaction. Okay, so what we're doing is we're going from, obviously we're starting from this this amide molecule here, which this is the amide, and we're effectively breaking that, and we're forming a carboxylic acid group on here, and obviously our amide molecule here. So what we need to do is we need to heat that with some dilute hydrochloric acid or sulfuric acid. That's the way in which we break up amides to form our carboxylic acid. So right, so we'll just put that on there. Okay, so we're going to heat that in dilute HCl / H2SO4. There you go. And so that gets you 1 mark for that first bit there. Okay, so let's just mark that on there. 1 mark. Good. Right, and then it says B part 1, how many stereoisomers are there with the same structural formula as piperric acid, including piperric acid itself? Right, this is a bit weird. So we've got here's our acid here. Now, when it's talking about stereoisomers, we're looking at things like EZ because we have some double bonds in here. Now, this is showing 1 conformation already, so it says including it. For every double bond that you have 2 different combinations. You have either an E version or a Z version. So this one is going to be 2 for this one, so that's 2. And then we have another double bond. This one can be E and Z as well. So because we have 2 double bonds and each one can have 2 conformations, then effectively we have 4 different possible isomers in total. So we're just going to put 4 isomers there. So yeah, just think about it in terms of that, and it'll make it a little bit easier rather than trying to physically work them out. Okay, and then it says draw the skeletal structure of a stereoisomer of piperric acid different to the one shown above. Right, now what I've done to save a bit of time, because these, obviously there's loads of different options here, is I've drawn them out already. I'm just going to try and explain how that works. Right, so if I just bring that in there. There you go. Right, so there's our different formations. So obviously we've got the 4 isomers and we've got the sulfuric acid. So here we've got different conformations. We're just going to briefly talk through them, which one, like how they're drawn. So you can see here what we've done with this one is now trans at this double bond, because we've got 1 and then 2. So these 2 are like trans from each other, you can see. So that's trans. But then this one, the second one, is cis, because we've got 1, 2. Both of these groups are pointing downwards. This one is cis-cis, so that means we have 1 and 2. So both of these are pointing down across this double bond. And this one, both of them are pointing up, so on the same side. So that's both cis-cis. And this one is cis-trans. Both of these ones are pointing down here. And this one is now going trans. It's opposite, you can see there, opposite the double bond. So any one of them would get you the mark there. Yeah, make sure that you're drawing them correctly, and they must be skeletal as well. We can't be drawing them in any other form because they've specifically asked for skeletal, so make sure you've drawn them in such a way as well. So just to save time, I thought we'd draw out all 3 different types there for you. Okay, right, and then on to part 3. Let's just nudge that up there. There you go. Right, so suggest structures for the compounds that would be formed when piperric acid is treated with an excess of hot concentrated acidified potassium manganate. Right, now what this does is we have this massive long molecule here that's attached to our so this is piperric acid. So we've got this molecule here, this huge hydrocarbon here. When we treat this with potassium manganate, and this is attached to a benzene group here, or an aryl group, which is this one here, then what happens is this effectively is cleaved off the aromatic group, and we have a carboxyl group here, C double bond CO2, sorry, CO2H, which effectively breaks this. So this happens when we have benzene rings and alkyl groups attached to them. If we heat it with enough heat, and we have enough heat on there, and it's excess as well, we have lots of potassium manganate, we'll also form carbon dioxide as well, because the excess bit's important. So as you can see there. So what we will find is we will form this molecule here. Obviously we have our two oxygens there. And then off here we have our C double bond O, OH. So that's the first one. And we also form carbon dioxide. We are heating it in excess, so we will produce this product here as well, which is carbon dioxide. So yeah, we need to obviously mark this up, one there and one there. Now, permanganate is an incredibly powerful oxidizing agent. So it has this ability to effectively break that alkyl group off the benzene molecule there and form this compound. So it's really, really powerful, and it's excess. So we get the carboxylic acid group that's formed on the end there. Okay, so yeah, okay, so let's move on to the next bit. Right, C part 1. Let's just drag that down so we get into focus. Right, it says write the expression for Kw. Okay, so it's a pretty straightforward expression. You just need to remember it. Kw is the ionic product of water. So this is the concentration of H plus times by the concentration of OH minus. Very useful for working out the pH of bases. We can use the Kw. And then it says use the expression and the value of Kw, well here we go, in the data book to calculate the pH of 0.150 moles per dm cubed sodium hydroxide, which is aqueous. Right, so what we have to do is we're going to take the concentration of the hydroxide ions. It's a strong base, so we assume that the concentration of this equals the concentration of OH minus ions. So we need the concentration of OH minus because this is going to play a part in our Kw. And what we're going to do is we're going to try and work out pH, we need to know the concentration of H plus. And then we can put that in our pH expression to work out pH. But we need OH minus and we need Kw. So that's what we're going to do. So let's rearrange this. Concentration of H plus is going to be Kw divided by the concentration of OH minus. And Kw at room temperature, which we're assuming this is, and all the conditions are the same, is 1.0 times by 10 to the minus 14. Now you will find this in the data book, but that's the standard value. And the concentration is obviously 0.150. And that will tell us the concentration of H plus ions in our solution. So 1.0 times by 10 to the minus 14. Divide that by 0.150, and we should get this massive number here. So I'm just going to round that. There we go, 6.67 times by 10 to the minus 14. Then once we've done that, we then need to work out pH. So pH equals the minus log of H plus. H plus is 6.67 times by 10 to the minus 14. So let's just grab this, put this in here. So the minus log of 6.67 times by 10 to the minus 14. And that gives us a value of 13.18. Let's round that up. There you go. And so you get 2 marks for this. You get 1 mark for obviously working out the concentration of H plus. So obviously being able to rearrange that Kw expression, and then 1 mark for pH as well. So there we go. Okay, so the pH of a 0.15 moles per dm cubed solution of piperidine is 11.9. So here's your piperidine here. So it suggests why this answer differs from your answer in C part 2. What we need to say is that, remember this is a very strong base here. And bases are proton acceptors. This is obviously a stronger proton acceptor than this here. And basically, the stronger the proton acceptor, the stronger it is, or the better it is at accepting protons, the stronger the base is. So obviously this one, this piperidine, make sure I spell it right. That's right, yeah. Piperidine is a poorer proton acceptor. So remember, it has this lone pair of electrons on the nitrogen there. So this is going to accept the proton, but it's not very good as a proton acceptor in comparison with sodium hydroxide. All right, and then on to the next bit. It says, how would you expect the basicity of piperidine to compare to that of ammonia? And we need to explain our reasoning. Right, now we're comparing it against ammonia. I'm just going to draw a diagram just down here just to kind of explain it. So we have ammonia here. Ammonia is NH3. There you go. It has a lone pair of electrons on the top. This piperidine has a lone pair of electrons here. I'm just kind of drawing them on there. But what we have is we now have two alkyl groups that are now like pushing electrons onto this nitrogen, or pushing electrons in towards it. So this means that these electrons are actually are more readily available. So therefore it will accept a proton easier than ammonia will, because it doesn't have any alkyl groups attached to it. So we don't have this availability of electrons as easy as we do in piperidine, because we have the piperidine, because we have two methyl groups here. You can see 1, 2 pushing electrons in, making these more readily available. So let's write the answer down on here then. So we say it's more basic than ammonia. Due to electron donating alkyl groups. Right, so in terms of marks, we obviously get, if I just come back up to here for this KW1, because we obviously get a mark for working out our KW expression. We get a mark for this one, and we get a mark for that one as well. So in total, we get 5 marks for the whole thing. Okay, right, so on to the next part. Go. Right, so part D. Let's just drag that down there. Right, it says part D, 20 centimeters cubed of 0.1 moles per dm cubed HCl was slowly added to a 10 centimeter cubed sample of 0.150 moles per dm cubed of piperidine. Or piperidine, however you say it. Right, the pH was measured throughout the addition. Right, so we've got to calculate the number of moles of HCl remaining at the end of the addition. Right, so what we're going to do is we're going to work out how many how much HCl we had at the start, and then obviously we then work out how much we had at the end, because all of the HCl would have reacted with that piperidine as well. So let's just put this on here. So the HCl at the start. Okay, so this is going to be, obviously that was the strength of the HCl, so it's going to be 0.10. And we're going to multiply that by the volume that was needed, which was 20 centimeters cubed. So it's 20 times by 10 to the minus 3. This is effectively converting this 20 centimeters cubed again into decimeters cubed. So normally we divide that by 1,000. That times 10 to the minus 3 is the same as dividing by 1,000. So that's why I put that there. And then obviously we're going to put that on our calculator to work out how much we have at the start. 0.10 times by 20 times by 10 to the minus 3. There you go. 2 times 10 to the minus 3. Right, and then we need to work out obviously how much we have at the end. So HCl at the end. Obviously after we've mixed them, the two together. Right, so we're going to take this amount that we had at the start, which is 2 times 10 to the minus 3. I'm going to subtract that away by how much actually reacted. Now, we said we had 0.150 moles per dm cubed of our piperidine, and we have obviously 10 centimeters cubed here. So we're going to do exactly the same. We're going to work out the concentration of piperidine, because obviously however much of this we've got, the number of moles, sorry, of piperidine we've got will tell us how many moles of acid was used up to react with it. So let's just quickly work that out. So I'm just going to put in 10, because that's the volume. Divide that by 1,000. And we're going to multiply that by the concentration, 0.150. And that gives 1.5 times 10 to the minus 3. Okay, and then if we put that into our calculator, so it's going to be 2 times by 10 to the minus 3. Subtract that away from 1.5 times by 10 to the minus 3. And that's going to give us 5 times by 10 to the minus 4. That tells us the number of moles of HCl that reacted. 5 times by 10 to the minus 4 moles of HCl. Okay, right, it says hence calculate the concentration of H plus and the pH at the end of the addition. Right, now this solution, this whole solution, obviously we added 20 in here and 10 here. We have 30 centimeters cubed of the solution. So that's really, really important. So we need to work out the concentration of HCl at the finish. Okay, so we have, let's just put that over there just to remind us. We have 30 centimeters cubed in total. It's very important. So the concentration of HCl, okay, at the finish is effectively the number of moles divided by the volume. So the number of moles that we had at the end here is going to be 5 times by 10 to the minus 4. And that's going to be divided by the volume. Now our volume is going to be 30, because it's 30 centimeters cubed. Again, divide that by 1,000 to get that into decimeters cubed. So that's times by 10 to the minus 3. And then if we bring in our calculator back in, so it's going to be 5 times by 10 to the minus 4. Divide that by 30 times by 10 to the minus 3, because that converts it into decimeters cubed. And we should get 0.016. So I'm just going to put on there, I'll put that in standard form. So that's going to be 1.6 times by 10 to the minus 2. To prefer it in standard form, you can leave it as decimal if you want. And this tells us obviously the concentration of HCl, but because it's a strong acid, we assume that the concentration of HCl equals the concentration of H plus ions. So therefore we can then work out the pH. So pH equals the minus log of this number here, 1.6 times by 10 to the minus 2. And let's just bring that back in. Stick that number in. There you go. Minus log 1.6 times by 10 to the minus 2. And there we have it. 1.79. Or should we just go for 1.8? Or we can round it up however you want, really. So I'll just put it in as 1.79. And there we go. And that's the pH afterwards. Right, and then it says, on the following axis, sketch how the pH will change during the addition of a total of 20 centimeters cubed of 0.1 moles per dm cubed HCl. Mark clearly where the end point occurs. Right, so this end point is going to occur at about 15 centimeters cubed. So we have a total of 30 centimeters cubed that has been added, so the end point is going to be 15. So we're going to start at one particular point here. Now remember the pH, it can't be anything higher than the pH of the base. Now we were told, we worked out that the pH can't be anything higher than 11.9. So if I just bring this bit back in, let's try and find it. There we go. Right, so if I bring that there, you can see it's 11.9 there. So you can say, obviously, we start off at 11.9 and we're going to add the acid to it. And the acid is obviously going to make it acidic. But again, the acid can't drop anything lower than this one here, because this is the pH afterwards. So we've got to make sure that actually this doesn't change. So we're going to start from here. and obviously it'll slowly decline very, very, very gradually until it gets to the 15 mark, and then it will drop massively, but it will not go any lower than this one here because our total pH is 1.79. This is about pH of 2, which is here. So really it can't go much lower than that, but it can't because that's that number. So you can't draw it all the way down. It can't be any higher than here because we said it was 11.9, so it can't be any higher. So we get 1 mark for making sure that this is drawn here fine. The end point, which is here, and then this bit here. So you get 3 marks in total. And I should also point out for these ones that you also get 1 mark for this, and you get 1 mark for that one as well. Okay, so once we've got our graph drawn, then obviously it's asking us about the indicator, which is probably the natural thing for it to ask. It says, from the following list of indicators, put a tick in the box by the side of the indicator most suitable for this titration. So we're looking for an indicator that changes within the endpoint range. So 0 to 1 will not change because it doesn't even go down to that low anyway, as you can see. So 3 to 4, that's pretty okay because we've got 3 there and we've got 4 which is up here. So that will change within the endpoint. So that's fine, that one. 11 to 12, again, it's too high up. You don't want it changing up here. You want it to be changing in the endpoint. 13 to 14, certainly not. It doesn't even get to that high. So actually the answer's got to be B. That's the indicator we're going to use. And again, you get 1 mark for that one there as well. So there we go. Another 16 mark question. So yeah, on to question 4. Okay, so this is question 4. And it says noradrenaline is a hormone and a neurotransmitter which is released during stress to stimulate the heart and increase blood pressure. You may have some of this in your exams. So yeah, this is the chemical noradrenaline, which they've given us here. And it says, state the names of 3 functional groups in the noradrenaline molecule. Right, okay, so the 3 functional groups will be alcohol, which is one of them here. We've got actually 3 of them here. Actually, we've got some 3 alcohols, so we'll put alcohol there. That's probably the first one that you would perhaps notice. And then we've got amine, which is here. This is the NH2, that's the amine along there. And then we have this, which is obviously quite big, which is the arene. All begin with an A. So arene, if I can spell it properly. Or you can say benzene molecule, anything like that. That's fine. Okay, so there you go. So we've got the 3 functional groups in there. Right, on to the next part. Okay, so we have, consider the following 2-stage synthesis of noradrenaline from dihydroxybenzene or benzaldehyde, which is this one here. And then it goes on to say, draw the structure for the intermediate Z in the box. Suggest reagents for steps 1 and 2. Right. Okay, so we're going to form, obviously going from your aldehyde here. And the aldehyde is then going to be converted. Obviously, we have an alcohol here. So this has obviously been reduced at some point. So we need to get the alcohol in there. But also very important, it's the big giveaway, is the NH2 here. So to get a nitrogen here from an aldehyde, we need to add cyanide to this, and the cyanide will then obviously will help to reduce the aldehyde, and then obviously you'll form your NH2 here eventually. Anyway, so the intermediate is going to be this. So we'll draw the benzene first, and then we'll draw what's coming out from it. So with the OH here, these haven't changed. The OH there, and then coming off this one here, we have, I'm just going to draw it here. I'm going to put hydrogen there, okay, and then here we have an OH, and then here we have a CN, and all of this is bonded to this carbon in the middle here. So that's the first bit that we need to be able to do, and then obviously this will then you'll add hydrogen and nickel, and you'll form your NH2 there. Right, and then obviously, well, we'll have to do that now anyway. So it says we need to say what's going to happen at step 1. So step 1, obviously we add hydrogen cyanide, HCN, and add sodium cyanide, or you can use HCN and a base, and that will help to form this compound. And then for step 2, Obviously we have to add the NH, so we're going to add hydrogen and nickel. That's probably the most common one. There are other ones as well. You can put in something like a reducing agent, lithium aluminium hydride, which is that one, or you can add sodium and ethanol as another one as well. But marks, right, so we've got quite a few marks on this page already. As soon as we're straight in, we haven't even really done much of the question. You get 1 mark for each of these, which is pretty good. We get 1 mark for us to draw on this molecule here, and then we get 1 mark for each of the conditions that we need to mention there. So already we've got 6 marks straight in. Right, okay, on to the next page. Right, okay, so it says dihydroxybenzene benzaldehyde reacts with Br2. Describe what you would see during this reaction. Okay, so when it reacts with this is quite an open molecule, so it's weakened in terms of the benzene structure. But when we add bromine to this, it will decolorize it because it will add onto the well, you'll have a substitution reaction, and it will go onto the benzene ring. If I can get my words out. Right, so this is bromine. And bromine will decolorize. Or you can say it goes from like brown to colorless, anything like that. Right, and obviously we then asking us to draw the structure of the product, which is probably what we should expect. So let's draw it out here. There's our 2 OH groups on the end. Right, and then we had our aldehyde, because that's what it was. That's what it's talking about. And the bromine would add maybe here or here. It doesn't really matter. You can have a 3rd bromine there if you want. Yeah, effectively decolorizes it because you form a compound which doesn't have a color. So, right, you get a mark for each of them as well. So you get 1 there and 1 there. Okay, right, on to the next bit. Then say C, draw the structures of the products when noradrenaline is reacted with dilute NaOH. Right, so let's just bring in this noradrenaline molecule again. Right, so we're going to react that with dilute NaOH, which is sodium hydroxide. So the sodium hydroxide is going to react with your OHs, which are going to be on here. So we're going to get a reaction there. And the sodium will actually react with the OHs on the benzene here. And you'll form your sodium salt based on these alcohols here on the end of the benzene. So let's just write our product down. So let's draw our benzene, which is here. You have an O minus, and it's your preference really where you want to put the charges in. I just put them in to show that it looks, obviously because it's ionic. And then we just have the rest of the molecule. I have an OH there, and H2. There you go. And so that's the ones that it will react with there. And then it says dilute HCl. Okay, so obviously this is going to go for, this is going to react with your, I should point out as well that it will only react, the sodium hydroxide will only react with these OHs because these actually act as acids. With them being on the benzene ring, they're effectively like a phenol, so they're a weak acid. So that's why it reacts with this and not with this one over here. So, but react with a HCl, obviously this is an acid, and this is going to react with the base part of the molecule. So the base part of the molecule is over here, so it's the NH2, so it's going to react with that only. So let's draw out our molecule, and it will react to form a salt. So let's just draw that here. Obviously, we still have our OHs as normal on that side, which goes there, and then okay, we have our OH there. That's unaffected as well. And then here at this bit, we have NH3, positive charge on that nitrogen because it's got 4 bonds, and then a Cl minus is also going to be attached there. So we're going to form this ammonium chloride compound here, which is your salt. Okay, and then That's that one. And then the next one, it says an excess of ethanol chloride. Right, so ethanol chloride can react with a lot of things. It's incredibly reactive, really corrosive, really toxic, quite a nasty chemical actually, but nonetheless incredibly reactive. So it's going to react with a lot of things here. So let's just bring our molecule back. Now it will react with the alcohols and it will form esters. So it'll react with all three alcohols here to form an ester in all three. And it will also react with your amine here and it will form an amide, which is what it'll do when it reacts with an amine, which is that bit there. So right, so let's draw up the molecules. There's going to be quite a lot going on in this one here. So we're going to draw, okay, we're going to try and draw it as best as I can. Give yourself plenty of space. See, because this ammonium chloride, this ethanol chloride is really reactive. Right, so the first thing, let's draw our esters here. So we're going to have I'll draw it out displayed so we can see exactly what's going on. Right, so we've got the C double bond O, and then CH3 on this side here. And then here we have exactly the same. So we'll just put C double bond O, oxygen, CH3, which goes there. And then we're going to draw a line going up, and then a line going down, and a line going up. And so here we also have the same as well. We have an oxygen bonded to a carbon with your double bond oxygen, which is going to go there, and then your CH3 on the end. So that's effectively that's your ester there. And then this one here, we have a nitrogen with a hydrogen coming down here. And this is going to be your amide. C, double bond O, it's going to go there, and the CH3. And the reason why I know it's CH3 is because this is obviously the group that's been added on, which is here. And then the carbon with the oxygen has obviously been added on here as well. So we've got the two carbons on each, as you can see. 1, 2, 1, 2, and then 1, 2. So we've got two carbons. So make sure you're counting for all the carbons on there. And so that is your molecule there. So it's pretty aggressive. It's pretty much reactive to everything. Right, you get a maximum of 3 marks for this one, up to 3 marks. So you get 1 for drawing these groups correctly, 1 for converting that alcohol correctly, and then 1 for obviously making it amide as well. Now there is, if I just go back up, we've got a mark here and a mark here as well. So you can see here that we've got 5 marks in total for all of these ones here. You only get a maximum of 4. So again, obviously they won't give you all 5. If you got all 5, then you're only limited to 4. So that is quite important there. Okay, right. So what it means is if you get one of these wrong and you get all this right, you get obviously all the marks. So it's quite an advantage in that way. Right. Okay, and then the next one. It says, name the new functional groups formed in reaction C part 3. Right, so the new functional groups, obviously, we've formed an amide, which is this molecule over here. So we're going to put amide there. And we've also formed an ester, because we've got 3 esters there. So we've got an ester. Right, and you get 2 marks for that. So obviously 1 for each. 1, 1. There you go. So 14 marks in total for that one. Right, that's it. On to question 5. Okay, so this is question 5. And question 5 says the 2 compounds V and W are isomers with the molecular formula C4H8O and show the following properties and reactions. Okay, so these both compounds react with sodium metal and both decolorize bromine water. So that could be potentially the sign of alcohol groups if it reacts with sodium or H, and decolorizing bromine water is a sign of an alkene. So just trying to work out what they might ask. It says compound V forms a yellow precipitate with an alkaline aqueous iodine, whereas compound W doesn't. So this could be a sign of, I don't know, like an alcohol, secondary alcohol, or even an aldehyde, perhaps. So anything like that, because obviously that would form this yellow precipitate. It's a classic sign there. And it says when reacted with cold potassium manganate, both V and W produce the same neutral compound, X. So obviously when we're reacting it with cold potassium manganate, because it's not warmed up, we will just form our 3, effectively some alcohols in there as well. So this might be a good sign because this is normally formed when we have alkenes. So when we react alkenes with this, we form alcohols. Now the fact that it's got 3 in there, 3 O's, suggests that we may have 3 alcohols perhaps. don't know, we'll think about it. And then it says both V and W exist as pairs of stereoisomers. So these are things like EZ, optical isomers, etc. Okay, so there's a lot to think about here. And then it says suggest which functional groups are responsible for the reactions with. And yeah, it's asking us about all these different things. So sodium, the thing which would react with sodium is the OH group. So yeah, that's what we need to put in there. So looking for OH groups. So we know that this molecule here must have an OH group in there. And there's only one oxygen there, so obviously there must be one OH group. But also it reacts with bromine water and decolorizes it. So this molecule, or these molecules, should we say, they must have a CC double bond, or alkenes. Also then, it says in alkaline aqueous iodine, so this is effectively discounted. There's two things here. You can either be an aldehyde, like a double bond O, test for carbonyl group, but we know it must contain an OH. So actually this means when we add it to aqueous iodine, it must mean it has that secondary alcohol in there. So CH3, CHOH. And this is the iodoform reaction, and you may have heard of that at school. But crucially, this one, V will form this compound, but W doesn't. So V must have this secondary alcohol in here, and W must not be a secondary alcohol. It must have an alcohol in, but it's not a secondary one. So in other words, it's got to be primary. So, but both will have a double bond in there. But crucially, when we react it with cold potassium manganate, effectively we've got to have 3 alcohol groups. So we've got to be very wary where this double bond is going to be in both of them. So we get 3 marks for this anyway. So let's just top the marks up here first before we draw the structures. So you get 1, 2, and 3. Okay. So then what we have to do is obviously suggest the structures for V and W. Right. So we know that V had to be the secondary alcohol. It has the CH3CHOH bit in there. So let's start with that bit first, I suppose. CH3CHOH. So we must have that bit in there. And then obviously we've just got to fill in the rest. This molecule has 4 carbons and it had 8 hydrogens in total. So we've got 5 hydrogens there. So that only leaves us with CH double bond CH2. We must have an alkene in there. It must have an alcohol in. V did react with iodine to form this yellow precipitate. And we've got to be able to form 3 OHs. So this double bond, because when we react it with the potassium manganate, our 3 OHs must be able to be formed. So we've got an OH there, and obviously an OH can be formed there and there. So that would be V. That would suggest V. W, though, the OH has got to be on the end because we said it's a primary alcohol. And again, we've got to form the 3 OHs when we react with our cold potassium manganate, but also it's got to exist as a stereoisomer as well. This one can exist as a stereoisomer. Let me just go back to this one just for a moment. If I just draw out the molecule here, just down below, so I'll just notice that up there. So we have the CH3 there, CH and an OH, which is there, and then we have CH double bond CH2. Now, obviously, we don't have any EZ isomerism here because we've got these 2 hydrogens on the end. What we do have is a chiral center, and it's there. We've got a hydrogen, an OH, a CH3, and the alkene. So this will have stereoisomerism. So that's why we can actually form this structure here with this secondary alcohol in place. That's the only structure we can have. Whereas with W, we've got to have an isomer, but the alcohol is going to be on the end this time. So in terms of the structure, we've got to have some kind of stereoisomerism with a terminal alcohol in the end. So this could be obviously EZ. So we're looking for things like maybe like a hydrogen up here, and then your CH3 down here, and then up here we're going to have a hydrogen there, and then down here you would have perhaps your CH2 OH. So this is your primary alcohol, which is here. So if I draw the structure of it here, so that's going to be CH3, CH, double bond in the middle, CH, CH2, OH. Must be primary alcohol. Must show some kind of stereoisomerism. So this is the EZ. So this conformation does. If the double bond was at the end here, it wouldn't have that conformation. So it can't form any optical isomerism because the alcohol's on the end here. We know it has to be on the end. So the only type of isomerism it can form is the EZ isomerism. So that's why the double bond must be placed in the middle here and not at the end, because you wouldn't get any EZ there. You can see these can flip round as well to form that. So this is a pretty tricky question. You really have to think about all the different bits of information they've given you. But we get 1 mark anyway for this, and then 1 mark for that as well. So we get 2 marks for that one in total. Okay, right, so onto the, let's just peel that one away. All right, okay, so this is C, and it says state the type of stereoisomerism shown by compound V and draw the structures of the stereoisomers. Right, so the type of stereoisomerism we've established is optical isomerism. So we're just going to put that on there. There you go. And then what we have to do is then we have to draw our structures of our molecules. So our stereoisomer, when we drew it out last time, but I'm going to draw it like this because sometimes it's easier to, well, we have to because we need to draw the mirror image. So we're going to have the CH3 up there, the OH, hydrogen down here, draw a wedge there, and that's going to be our CH double bond CH2. So if I just bring that back in, I'll show you where that's come from. There it is there. So you can see we have our chiral center in the middle there, hydrogen coming off one, OH coming off the other, methyl coming off one, and then your alkene or your ethene here coming off the other. So you can see there, hydrogen, alcohol, methane, alkene. Okay, so that's that one. And then all we have to do is just draw its mirror image, which is pretty straightforward. So we're just going to put the carbon there. We're going to put the CH3. So put the CH3 there. The OH this time is now going to come over to this side. So it must be a mirror image, as you can see. Hydrogen there. Wedge coming out there. And then CH2. Or CH2, should I say. So there's your double bond. Right, as you can see, this is a mirror image of that. So that's why, and all optical isomers are chiral, so they are mirror images of each other effectively. Okay, right. And then the next one, it says suggest the structure of the neutral compound X. So this is the one where we add the cold potassium manganate solution. What happens is if you have an alkene, it will form OHs. If it was warm, then you would get further oxidation and it would go to ketones and a carboxylic acid. But because it was cold, we'll just get the 3 alcohols. So compound X, remember the formula for compound X was C4H10O3. So we're going to have 4 carbons here. So we're just going to draw in 1, 2, 3, 4. And remember on the end, we had the alcohol already. So this was an X, remember, was formed when both V and W, they produced the alcohol. So if the alcohol was already there, then we don't need to add it. So in one of them, we had an alcohol at the end. So that was for W. But V had the alkene on the end as well. So that would convert into the OH. And then we'd have an OH here, which is on this one, and we'll have an OH there. And again, let me just bring back the molecule so you can see how this has come about. So you can see here, if we did that with V, you would have an alcohol here and an alcohol obviously here, and then there's a one in the middle already. And then if it was W, the alcohol's already there already, and you would have 1 and 2 just on the end there. And that's exactly what we have there. There's our 2 alcohols. on the adjacent carbons next to each other, and then we have the OH already on the end. So you get this molecule here. Again, it's a pretty tricky question. There's a lot going on there. You get 8 marks in total. Let's just quickly mark these up that we've got so far. So we have 1 for the optical isomerism at the top there. You get 1 for this here, and you get 1 for that one, for that final molecule there. But there's quite a lot going on there. I have to really think about that one and make sure that you're getting them all correct. Okay, but it's a short question. So let's move on to question 6. Okay, so this is section B, and this is question 6. And this is, you may be thinking that this looks like a biology exam, and this is the biochemistry bit where we're looking at DNA. And it says, question 6 is proteins and deoxyribonucleic acid, which is DNA, are 2 important polymers that occur within living organisms. And it says, A, proteins have a number of levels of bonding, primary, secondary, and tertiary. There's also other ones, quaternary as well. This is just complete the table to indicate the level of bonding responsible for the features described. Right, this is pretty much, you just have to try and remember these. It's very important that you're able to identify different features of the different levels of bonding in DNA. These are horrendously complex molecules, so they try and split it up into the different sections. What we're going to do is going to try and identify them, obviously in order. And primary starts off with a very intricate, literally building of the smallest bits, which is the amino acids, joining them together to form the long protein molecules. And the proteins will then wind themselves into this different form as helix, as like a double helix, or like a twist, or you can get layers, you can get different things like that. So that's the formation of that. And then once you've formed that, the third level of bonding is effectively talking about how these twists can hold themselves together, or the layers can hold themselves together with different types of bonds. So they're your different levels. So let's look at what we've got here. So we're talking about this formation of the alpha helix. Now, because we're talking about the formation of the alpha helix, this is the secondary level of bonding. So this is where you've taken your proteins and we're starting to form it into some kind of specific shape. So this is secondary. So it's not quite as small as the amino acid one, which we'll come on to in a minute. Okay, so this one's secondary. Secondary. There we go. Okay, and the formation of disulfide bonds. So this is actually after you've made your alpha helix. These helixes are then effectively attached to each other, or they hold their shape by some bonds and interactions. So anything to do with bonding and holding these shapes together is obviously a tertiary structure. So we've obviously looked at the shape of the helix, and now we say, right, how are they bonding with each other? So we're like zooming out even further. So this is tertiary. This is a tertiary level. So is this one as well. The ionic bond is also tertiary. Anything to do with bonding in terms of the structures, the alpha helix, etc., is going to be tertiary as well. And then the linking of amino acids. This is the most intricate part. This is the smallest bits that we're going to talk about. So this is what makes up protein. So this is going to be primary. This is very, very, very detailed. So we see this as the primary structure. That's the first bit we talk about when we're talking about the structure of DNA. So you get 3 marks for all of that. So yeah, you've just got to make sure obviously you're aware of the different levels of DNA bonding, of the DNA structure. So you get 3 marks for that. Okay, it then continues, and we've got something like this. Let's just draw it here. The diagram shows part of a DNA molecule. Study the diagram and give the correct names for the blocks labeled J, K, L, and M. So this looks like, I'd like to describe this, it looks like dolly mixtures. Normally you build up bits of DNA in schools using dolly mixtures and little cocktail sticks, etc. So you can, this effectively looks like the same. You've got these circles and squares and rectangles, and they're just representing different parts of a DNA molecule. Right, so this is just examining you on your understanding of it. So we'll have to look at the different letters. So we'll look at J first. Now J is obviously bonded to one of the bases here. Now the bases are attached to sugars, and the proper name for the sugar is deoxyribose. This is in a DNA molecule. So we're going to put J as your sugar. So put deoxyribose. Okay, and these sugars, we'll just look at L because it's attached to it. These sugars are actually joined in between the two different sugars, are joined by phosphate. This is the phosphate backbone, so this is the L. So L is actually the phosphate. Okay, so obviously that's attached there. And then we have to look at our bases. These K and M are the bases. This is like our different thing, our different like rungs of the ladder, effectively, these ones here. And this is like the kind of the backs of the ladder, effectively. So we've got this double helix strand here. The bases sit in between. Specific bases pair up in specific ways. So for example, G, there's 4 letters that you need to know for DNA, which is G, C, and A and T. Now G and C go together, and C stands for cytosine. I don't know, one of the ways which you can remember it is something cheesy, perhaps like dough chemistry, or chemistry's great, or something really, really cheesy like that. You know, really, you can think of whatever you want, and as long as you remember that G goes with C. For those biologists out there, they may be able to remember that anyway. But yeah, G always goes with C, so that would be C is cytosine, which is K. So cytosine. And M, this one, A, adenine, will always react with a T, which is thymine. Again, you can kind of remember that as maybe something like the A team or something like that. So A and T, which is A team. So A and T always go together, so T is thymine. So yeah, anything kind of cheesy or thing like that, if it's obviously going to help you to remember it in the exam, then who really cares? So, right, we've got 4 marks there. So, you know, loads of marks for remembering the structure of your DNA. So, yeah, there you go. So you get 4 marks there and then 3 there. So quite a few so far. Right, on to the next part. Okay, so then, let's just drag that down there. Okay, so then it starts talking about, it says the DNA molecule is formed from 2 polymer strands which are held together until DNA replication occurs. So obviously this is in the nucleus of the cell. It then says what type of bonding holds the strands together. This is hydrogen bonding. So you've just really got to know that one. It's always hydrogen bonding. Alright, okay. So explain why this type of bonding allows the base pairs within the strands to separate during replication at normal body temperature. Now, what we need to say is obviously the hydrogen bonds are quite weak. They're not really bonds, they're intermolecular forces. So these are quite weak, and so therefore we don't need much energy to break them, or very little energy is needed. So let's put that down in there. So the bonds are weak. So that's your first thing. And we need a little energy. Little energy is needed to break them. So yeah, so we get 2 marks there. You get 1 for saying, obviously talking about hydrogen bonding, and then 1 for talking about that as well. Okay. And then section D, or part D, it says in the polymer RNA, the identities of 2 of the blocks, J, K, L, or M, are different. For one of these blocks that are different, give its correct name in DNA and in RNA. Right. So there's certain things which are slightly different. So we need to identify what could be different in both of them. And effectively, the sugars are slightly different in either of them. So in this case, the sugar is represented by J in your diagram, if you look at that. And effectively, I'm just going to write this on here. So because there's 2 blocks, but I'll put them both on. You only need to give one of them. So the sugar J, in DNA, obviously, we've already labelled that as deoxyribose. But in RNA, obviously the D stands for deoxy, and the R just stands for ribose. So this is literally just ribose. So you might be able to remember it from that way. Okay, so that's what's slightly different about them. But also the base. Base. Now we're talking about M in this case. Okay, So in DNA, it's called thymine, okay, which is given the letter T. But in RNA, it's instead of a T, we don't have T in RNA, we have U, and U stands for uracil. So any one of them would get the mark. It's either going to be this one, either this one or this one. It doesn't really matter which one you pick, but you only need one of them though, and that would get you the mark. But I've put both on there to give you that option there. But there we go. That's the end of question 6, or biology, just a hint of biology there. Right, let's move on to the question 7. Okay, so this is question 7, and question 7 is looking at NMR, which can be a real pain sometimes, but we'll obviously you need to know it, so let's at least try and tackle it with this question. So question 7 actually starts with mass spec initially. So it says the combination of mass spectroscopy and NMR spectroscopy provides a powerful method of analysis for organic compounds. It says A, the mass spectrum of a compound G contains M and M+1 peaks in the ratio of their heights of 74 to 2.5. Use these data to calculate the number of carbon atoms present in G, and you've got to show your work in. Right. If you've got the CIE textbook, the big thick one, then if you turn to page 447, there's actually a formula that they tell you that you should be able to use for this, and the formula is effectively N, which equals 100 divided by 1.1, and that's multiplied by the relative abundance of each of the isotopes, and that should give you the number of carbons that are in this isotope. So what we're going to do is we're just going to use that formula that is on that page there. So this is going to be N equals, and we're going to have 100 on the top, times by 2.5, because that is the abundance here of the M+1 peak. So that's the abundance of the M+1. And that's 100 times by the abundance of the M+1, divided by, and it's 1.1 times by the abundance of the M+ peak, or the M peak, which is 74. And then obviously put the brackets around that, and then obviously we'll put that into our calculator. We should get our answer there. So that's going to be 100. Whoops, let's just put that into brackets. That might be quite useful. 100 times by 2.5, divide that by 1.1 times by 74 equals, and then we should get 3.07. If we round that, it's 3.1. So effectively G has 3 carbons, because obviously we've got a 0.1 of a carbon or 0.07 of a carbon. So this one, if I put N equals 3.1, so effectively G has 3 carbons. Okay, so you get 2 marks for this. You get 1 obviously using the right formula initially, and then you get 1 for suggesting how many carbons it has. So you get 2 marks in total for that. So again, not too bad. Okay, right, and on to B as we're coming to NMR. Right, so it says the NMR spectrum of compound G is shown. You can see here that we've got the spectrum here. Now, if we just take a quick look at the spectrum, see what we've got first, because if we know a little bit more about it, it might help us with the questions later on. You can see here that we've got 3 different types of peak here, and these 3 peaks tell us that we have 3 carbon environments, or 3 proton environments, sorry, because it's a proton NMR. So you have 3 different proton environments. The splitting here tells us basically how many hydrogens this environment is next to. So obviously this set of hydrogen environments is next door to 2 hydrogens, because we have a splitting pattern of 3. And according to this N+1 rule, the number of peaks, depending on the number of mini peaks that we get within this one here, within this signal, tells you how many hydrogens we've got. So because we've got 3 peaks here, that means we have 2 hydrogen environments next door to it. This one is a different environment, and this one is split into 4 peaks, and this tells you that this is next door to something with 3 hydrogens in. So which is pretty useful. And this one here is really well shifted up, so we'll find out what that is in a minute. But this one is as a single peak. So this tells you that it's actually next door to no other hydrogens, or not directly next door to it. So this could be a classic sign of maybe it's an OH or something, because normally OHs give you that single peak because they're next door to an oxygen, not next door to a carbon with a load of hydrogens on it. So that's just kind of giving us a little bit of an insight. We don't have any integrations on here, so we can't really work out how many hydrogens are on each one, but we do have the shift, which we'll use later on. Okay, so right, it says use the data booklet and your knowledge of NMR spectroscopy to identify the type of proton responsible for each of the 3 absorptions. Now, what I've done is I've actually, to save a bit of time, I've actually marked up the data sheets to try and work out what's in there. So if we've got the first one, which is 1.1, I'll just bring it over here. I'll try to use some little arrows to kind of show what's going on here. So you can see we've got 1.1 will suggest that we have an RCH3 group, a CH2 group, or a CH. So anything around there, you can see there's the chemical range there, which is 0.9 to 1.7. Now you may think, well, actually, if I come down to here, if I just move that just slightly further up, you can see the OH group as well. You can see the OH group also falls within that range as well. But the OH group, though, the problem with the OH group is that you would only get a single peak. And actually, we see this peak because of the hydrogen is obviously next door to an oxygen, so we get a single peak. Now you can see our peak at 1.1, which is what we had before this one. You can see isn't a single peak, so this can't be an OH for that reason. So 1.1 must be a CH3 or some kind of CH2 group. So anything like around there should be fine. Okay, so let's just put down RCH3. So anything like a methyl group or CH3 or anything like that. Right, and then we're looking for a peak at 2.2. And a big hint that this might be CH3 as well is actually this one here. It's got a split. We have a splitting pattern of 4 as well, so that could be a good sign that it could be CH3 as well. The next one, 2.2. Right, let's just again throw this back in here. Okay, the only one which would fit again with 2.2 is this group over here. So we've got an alkyl next to a carbonyl group, which is C double bond O. Again, the alcohol could fit into this as well that I showed you before, but again, because it's not a single peak that we've got, it wouldn't fit. So the only one that would fit is, because it's at 2.2, is this one here. So really, we're looking for anything with an alkyl group there. It could be a CH2 C double bond O or CH3 C double bond O. Again, due to the number of splitting patterns that we have, it's unlikely to be something like this because of the splitting we've got. So anything to do with CH3 C double bond O or CH2 C double bond O. Okay, so let's just write that down there. I'll just write down CH2 C O or anything like that. Okay, C double bond O. Again, I'm looking at the splitting patterns again in this here, and you can see we've got a splitting pattern of 3 and a splitting pattern of 4, which kind of suggests that we do have a CH3 and a CH2. Remember this one here, this CH2CO, is probably going to be next to a CH3 because it's split into 4. So these are probably actually going to be quite likely to be the actual answers here. So that's why I've gone for the CH2 C double bond O as well, because it seems to fit the splitting patterns that we've got. And then 11.8, right, so if we bring this back in, right, 11.8 shifted really high up. So I'm going to put these two down here. And you can see the 11.8. We have 2 options here, and it could be a RC double bond OH, which is a carboxylic acid group, because that fits into the 11.8 category, or it could be an amide group as well, which is 5 to 12. So that could fit into the 11.8 category as well. So actually, either of these could be possible. So I'm going to write down either one of them. So let's just pull that back. Again, we don't know at this stage what it could be. So I'm just going to put COOH, or we could have the amide group, which is RCONH. So anything like that. So either one of them will do effectively. So you get a mark for each one of these. So we get a mark here and a mark here, and a mark here. Okay, we're still really uncertain about this, probably quite certain about this due to the split in here, but this one that's shifted higher, we don't really know what this is. Okay, yet anyway. Right, so part 3, or the next one, part 2, sorry. The addition of D2O causes one of these absorptions to disappear. Right, explain why this happens and state which absorption is affected. So this is a bit of a giveaway now. When we add D2O, D2O actually is the isotope of hydrogen, so D is deuterium. It's an even number, and NMR can't detect even numbered nuclei. So what's happening is the D2O will actually substitute the hydrogen on an OH group, and effectively a peak disappears because the NMR machine can no longer detect even numbered nuclei. So this is actually a sign of an OH in there, and the only OH that we can have is from the carboxylic acid. So actually, when we looked at 11.8 before, this one here, this effectively cancels this one out. It discounts this completely. So when we add the D2O, it replaces an OH on the alcohol group, and the only one, obviously the OH group is only on a carboxylic acid. It's not on an amide. So we're going to write this down here. So the peak at 11.8 disappears because and this is because of the effect. We've got the OH/D exchange. So maybe to help illustrate this, I'll write an equation. So we have the ROH, which is on the carboxylic acid, and we're going to react that with your D2O, which is also known as heavy water, because obviously it's a heavier isotope. And effectively what you form is ROD. This is no longer detected by the NMR machine, and obviously you have HOD as well. So because this is no longer detected by the NMR, this peak at 11.8 effectively disappears, and it goes. That is actually a good sign of a COH and not this. So that's given us a massive, massive kind of help here. Also, this kind of cements this theory as well. We've got this carbonyl group. This is obviously a CH group directly bonded to this. So that's we're now starting to form our picture. So the NMR can be quite useful at times. Right, so now what we have to do is then obviously we have to draw our structure. Now, just coming back onto this, looking at our structure, we know we must have a carboxylic acid group. So I'm going to draw this over here. Now it has to be the structural formula. So we've got a carboxylic acid group, which is CO2H. And then next door to that, remember, we had a CH group that was bonded to it. See the CH group, which is here, this one here, bonded to the carbonyl group, what's next door to the carbonyl group. And we know that this peak at 2.2, is got to be next door to something with 3 hydrogens attached to it, which could be the CH3. And the CH3 itself has got to be next door to a carbon with 2 hydrogens on, which is this one. So this suggests that these two are actually next door to each other in the structure. So next door to this, obviously we have our CH2, which is going to be there, and next door to that is going to be a CH3. And so that is effectively propanoic acid. And so that is the formula that we've got. So you get 1 mark for the structure. So we'll put that there. Okay, right, and then part C. Say several structural isomers of G exist. Draw the structural formula of an isomer of G with only 2 absorptions in its NMR spectrum. Right, now there's quite a few of these, and we're looking for 2 absorptions only. So we're only looking for 2 proton environments. So, and it's got to be an isomer. So the first thing an isomer of a carboxylic acid would be an ester. That's the first thing that comes to my mind anyway. So, and we're only looking for 2 environments being produced. So there's one environment, there's another environment. So that would produce 2. Or we could have this one. Looks a bit weird, looks like some kind of alien. We have obviously our proton environments there. These 2 would be in the same environment, these ones here, because they are bonded to the same carbon. So these would be classed as one environment, and then you'd have some hydrogens here. And again, these would be the same environment as well. So this is an isotope. So that's that one. Or we could have this one. 2 oxygens there. So again, these two, there's hydrogens hanging off this one. These two be in the same environment. And then this one would be a different environment. So you'd have 2 environments there. Or you could have it the other way around. So let's put the ore there. Right, let's drop that there. Oxygen, that down there. Oxygen and a bond between them. Again, hydrogen environments, we've got 2 there. They'll be the same environment because they're bonded to the same, kind of doing the same kind of environment here. So that'll be one environment, and that's your second one there. So that would give you 2 as well. So any one of them would give you the mark, which would go there. And then on to the final thing. Now this obviously depends on the molecule that you've drawn. So what I'll do is I'll go through each of the peaks, and I'll just quickly tell you them. I've had a quick look at what these peaks will be on the table. So depending on which one you've drawn will depend on obviously the peaks, where the absorptions would occur. So let's start with methylethanamate, which is our ester here. You would get a peak at 2.0 to 2.1, and you get a peak at 3.3 to 4.0 for this one here. So if you're drawing that there, your answer's there. If you've drawn your dihydroxycyclopropane, which will be this one here, then you should get a peak at 0.9 to 1.4. This would represent these hydrogens here, the CH ones. And then you'll get a peak between 0.5 and 6.0, which would represent these alcohols here. If you drew 1,3 dioxylane, which is your 1,3 would be this one here. This is your 1,3 dioxylane. You would get a peak at 3.3 to 4, and you would get a peak at 3.3 to 5. And then if you draw this one, which is your 1,2 dioxylane, you would get a peak at 0.9 to 1.4, which would be this one here, and you'd get a peak at 3.3 to 4, which would be these 2 here, which are in the same environment. So it obviously really does depend on which molecule you've drawn to the types of peaks that you get. So please check to make sure them answers, to make sure you've got them right. Okay, so that's it. On to the final question, which is question 8. Okay, so this is the final question on the paper. This is question 8. So it's 8A. Many common drugs are taken orally, but some medications, such as those based on protein molecules, are injected to prevent them being broken down in the digestive system. So it says, number 1, name a functional group present in drug molecules that might be broken down by acid in the stomach. So really we're looking for a way in which we break things down using acid. So things like amides and esters are easily broken down by acids, so we call it acid hydrolysis. So we're going to break these up. So that's what we need to put on there, really. Anything like that. So amides slash esters. You could even put like peptides as well, anything to do with that, because they're like obviously in proteins. So yeah, not good if you're going to take a drug like that. Okay, and then it says state the type of reaction that would cause such a breakdown. Again, we call this hydrolysis. This is just breaking down of an ester or an amide using, obviously it was acid hydrolysis. So let's just put that there. Okay, right. So you get 1 mark for each one of them, which is not too bad. So you get 1 there and 1 there. Okay, right. And in part 3, it then goes on to show these massive molecules here. It says which one of the following compounds would not be suitable taken orally. So basically, we're looking for, if we eat them, it's going to get into contact with our stomach acid. So we're looking for molecules that don't have an amide or an ester in there. And well, effectively because it's not suitable, so we are looking for molecules with amides and esters, should I say. So you can see if we look in here, we don't have any amides or esters in this molecule, but we actually do in this one. You can see we've got an ester there. We also have an amide there, this molecule here, there it is, and the C double bond O, and you've got an ester here. So this one really wouldn't be very good, because if you ate that, these groups here would be hydrolyzed and they'd form into something else. This one is fine. It doesn't have any esters and it doesn't have any amides, so that one's okay. So actually, the compound that we wouldn't eat is B. So that's that one. And then it moves on to IV. It says, on the structure of your chosen compound in part 3, circle all the functional groups that might be broken down by the acid. Right, so we talked about this already. There's our amide, there's one there, and we've got our ester there, and we have an ester there. So these molecules, or these parts of this, wouldn't be very good, because these would be broken down. Right, we get 2 marks for this. You get 1 for identifying your esters, which are these 2, and you get 1 for identifying the amide, and obviously, well, 3 if you include the compound as well. So in total, you get 5 marks for all the ones on this page here. Okay, right, and on to the next bit. Okay, so this is talking about these hydrophobic and hydrophilic groups. So these are phospholipids in this case. It says, one way of protecting drug molecules that are taken orally is to enclose them in liposomes. These are artificially created spheres made from phospholipids, which have an ionic phosphate head, which is this bit here, and 2 hydrocarbon tails. So we've got one there and one there. Okay, which is pretty useful. Right, so it says, state and explain in which location, P, Q, or R, a hydrophobic drug could be carried. Right, so this drug is hydrophobic, so this would have to sit in a region which is also hydrophobic. On these groups here, the tail is a long hydrocarbon chain. This doesn't dissolve very well in water. In fact, it doesn't. It's pretty much nearly insoluble. It can't hydrogen bond with water, so therefore the tail group of this is classed as hydrophobic. So the drug would have to sit in a region where there's loads of tails, and this is going to be in Q, which is on here. So we're going to write that on there. So Q, and the reason why, as this is the hydrocarbon tails region, is hydrophobic. There you go. Okay, right. So there's your first one. Obviously, you get a mark for that. So yeah, that's just showed. Basically, it's just having an understanding of the tail group's hydrophobic, the drug's hydrophobic, so they need to go together. Okay. Part 2. By considering the nature of the functional groups in A, B, and C, explain why these drugs can be carried at position R in the liposome. Right, so the reason why, if I just bring all these compounds back in here, you can see they've all got oxygens and hydrogens, or nitrogens, or anything like that. So all of these can actually interact with the polar head group on your phospholipid, and because they can interact, that means that actually they can be held in the middle. In other words, in the interaction we're talking about is a hydrogen bond. Hydrogen bonding can occur wherever you've got these oxygens or nitrogens here, and so that means they can be suitable and they can go in the middle. Remember, the head of the phospholipid group, which are the heads here, these are the heads facing inwards, these can interact. It's like a little cage, really. So yeah, let's put this down here. So they all contain hydrogen bonding groups. Okay, so in this one, again, you get a mark for this as well. So you get 2 marks for both of these parts here. Okay, right, and then on to C. Okay, it says another method of protecting drug molecules is to trap them inside gold nano cages. Very posh. It says when they reach the site where they are needed, such as a tumor, the drug is released by exposing the site to infrared radiation. And it says part 1 suggests the size of the nano cages in meters. Nano really is 1 × 10⁻⁹. This is the size of it. Although you could technically go down to 1 × 10⁻⁷, anywhere around there is technically classed as nano scale. So yeah, you just got to remember them numbers, and obviously that would get you a mark as well. Let's write that in there. And then the last one, it says suggest why infrared rather than higher frequency radiation is used. Right, if we obviously radiated people with a higher frequency, the higher frequency would have more energy, and this is going to cause cell damage, which isn't good. Obviously, if you're detecting the tumor, you don't want to cause any more damage than you have to. So using a lower frequency would mean lower energy, so therefore it's safer to use. So yeah, anything higher than that, really, like for example UV, can cause damage. So a little bit of physics there. Okay, so can cause cell damage or mutations or anything like that. So you get a mark for that as well. And so there we go. So you get 2 marks in total for that. So that's 9 marks for that whole paper. So again, not too bad. Make sure you make sure you mark the paper correctly, and that you're able to obviously understand why these are going wrong. That's the whole point. And there's many more videos on my YouTube channel, not just these, but ones that go through content as well. So just click the subscribe button. There's a little subscribe button at the bottom right, or subscribe to the channel, and there's loads more videos coming up in the future as well. That will help you to finally get your head around chemistry and make sure that you pass them exams. That's it now. Bye bye.